So now you know what psi squared is. It's a probability density. Hey, you and I, we can understand that. Psi squared, we can understand that. It's a probability density. But what I want to really emphasize here is that it is a probability density. It is not probability. It is probability per unit volume. That's important. In a moment, we're going to look at a quantity that is a probability. But this is a probability density. All right, you got to get the units correct here. All right. So, how can we use that to understand something about where the electron is in an atom? So, probability density. What I'm going to do is I'm going to represent the probability density here by a density dot diagram. So I'm going to take my 1s orbital, okay, my 1s wave function, or my psi 100 wave function, and I'm going to square it. And then I'm going to take the results of that squared function and plot it as a dot diagram here, where the density of the dots is proportional to the probability density. So the darker the dots, the higher the probability density. And as the dots get more and more dispersed, right, the probability density is getting smaller. So I did that for my 1s wave function, squared the 1s wave function, and plotted it here on an x, y, z. Yeah. Oh, I got the x and the y turned around. Okay. That's all right. I plotted it here. What you can see is that the probability density is a maximum at the origin, at the nucleus, and that it decays equally in all directions. It's isotropic. There's no angular dependence. It's spherically symmetric. And that you can also see nicely if you look at the actual plot of the wave function, not psi squared now, the wave function, which I'm plotting here. This is the wave function, and I'm plotting it versus r. Actually, what I'm plotting it here is as r over this, something called the A naught. A naught's a constant. A naught is called the Bohr radius. A naught is about 1/2 an angstrom. I'll explain to you where A naught comes from in a little bit, but right now it's just a constant. Here's the actual form of that wave function. Okay? Hey, it's pretty simple. This stuff right in here, this is all a constant, right? Just 1 over pi A naught cubed. I said this was about 1/2 an angstrom. And then the important part is right here. It's a decaying exponential in r, e to the minus r over A naught. And so the wave function starts out at some high finite value at r is equal to 0, and it drops off exponentially as r goes to infinity. That's what we're plotting, and you can see that reflected here. When you square this, you can see that reflected in that probability density. All right? So what does it tell me? It tells me that the probability density is highest at the nucleus and drops off in an exponential fashion equally in all directions. This is spherically symmetric. So here, I plotted the 2s wave function. I took the 2s wave function, I squared it. And so I got values as a function of r. And again, the density of the dots is proportional to that wave function squared. And again, what do you see? You see that the probability density is largest at the origin. And that it decays, again, equally in all directions because it's spherically symmetric. And it decays so much that all of a sudden you get to some value of r, and there's no probability density. And then As you get to larger values of R, well, the probability density increases again, right here, right? And then it finally decays as you get to larger values of R. What this wave function has in it here is something called, a node. There is a value of R right in here where there's no probability density. That value of R in terms of this constant A0 is 2 times A0. We call that a radial node. You can see that radial node very easily if you look at a plot of the actual wave function. So we're not squaring the wave. This is the wave function. Here it is. Here's the form for it. At R is equal to 0, it's some finite large value, and it decreases. It decreases till we get to a value of 0. Psi is equal to 0.